Hello, I'm Steve Reyes from Anritsu, and in this presentation I'll be discussing the 220 GHz VectorStar broadband system. The agenda for this presentation is to first go over the system configuration and discuss some of the technology that was used in developing the mmWave module. We'll then discuss the interface solutions that we came up with in order to be able to connect the module directly to the probes. And then we'll show some examples of system performance and discuss some of the on-wafer probing challenges that one might encounter when probing up to 220 gigahertz and the alternative solutions that we make available. And then talk a bit about different configurations and different ways we can set up the system. So this is an example of this system configuration. We are using the VectorStar as the baseband VNA, and this particular model can sweep up to 70 gigahertz, but in the broadband configuration we only needed to sweep up to 54 gigahertz. So the VectorStar in this case is sweeping from 70 kilohertz to 54 gigahertz and then switching over to the mmWave test set. The mmWave test set routes the RF and LO signals to the nonlinear transmission line modules, which then provide measurements up to 226 gigahertz. And that module is connected to the probes, which then provide the on-wafer measurement capabilities. The compact nonlinear transmission line modules provide the opportunity to install on probe stations that might have smaller platens, so there's a wide range of installation options when installing the 220 gigahertz system. In addition, the compact module provides direct connection to the probes, thereby eliminating the need for cables and optimizing dynamic range and measurement stability. The probes that the module connects to are the MPI Titan probes, and they're available in 50, 75, and 100 micron pitch. MPI also offers calibration substrates that supports a wide range of calibration capabilities. The 220 gigahertz module provides a DC path back to the VectorStar baseband VNA. So VectorStar is providing the signal from 70 kilohertz up to 54 gigahertz and passes directly through the module to the test port. The module then provides the source bands, and those are coupled onto the main transmission line for best raw directivity, which gives you optimized measurement performance as well as calibration stability. The down converters are located close to the test port and operate from 30 gigahertz up to 226 gigahertz. So these nonlinear transmission line harmonic samplers are what provides the IF frequencies and sends those back to the VNA for further processing. And you can also notice that there is ALC control right at each of the source modules, so that we provide very wide power control with as much as 50 dB of range. Harmonic converters are often used in mmWave receivers. And usually what happens is the LO waveform in these receivers will be shaped in order to improve on the higher order conversion efficiencies and the linearity of the receiver. So the nonlinear transmission line technology provides aggressive shaping of the LO waveform in order to provide very good conversion efficiencies even at the highest frequencies. And that is the reason why the VectorStar broadband system provides excellent dynamic range even at the highest frequencies. The connection of the module to the probe is an important consideration for these broadband systems. Typically, we have had a 1 millimeter or a 0.8 millimeter threaded connector as the test port, and that will define the upper frequency limit of 110, 125, or even 145 gigahertz. In order to get to 220 gigahertz, then we would need to get to a 0.6 outer diameter connector, and that can be a challenge and will require a number of considerations. The direction we took in connecting the probe to the module is to use the 0.6 millimeter connector, but to use a UG387 flange for the alignment. And so using the flange that was designed for supporting 220 gigahertz connections gives us the repeatability and the alignment needed for these connections, but in this case we're using a male-female center pin connector. The other change and modification we made was to slot the male pin instead of the female pin. This gave us the advantage of better durability and reliability over multiple connections. The end result of this new design is a connector with very good repeatability over a lifetime of connections. In this plot we're showing the vector delta comparisons between initial and final results over 100 connections of a return loss device of about 10 dB, and you can see that at 50 dB it's providing very good repeatability and on par with the 0.8 threaded connector. So the overall system performance then is broadband measurements to 220 gigahertz with very good dynamic range and no sacrifice in performance at 110 gigahertz. As shown in the previous block diagram, we offer electronic ALC control. This ALC circuit is a real-time heterodyne ALC loop and can get down to the minus 55 dBm range, which is quite useful when characterizing active devices that need to be well within the linear region. Often the linear region can be far below minus 30 dBm, so having this amount of power control when characterizing active devices is quite useful. The end result is that we provide very good stability over temperature. This plot shows over a 24-hour period in a lab environment with 25 degrees plus or minus 3 degrees, good stability in terms of magnitude and phase. So for calibration, on-wafer calibrations are supported by the system, and we provide uncertainty curves for the general use of probes and calibration substrates. One aspect to keep in mind is that now that we're getting to these higher frequencies, using a calibration substrate on a ceramic chuck is quite desirable. On a metal chuck, you can find issues may end up being something that will create some uncertainties due to the multi-mode parasitic propagations. So if you have access to a ceramic chuck, that would be ideal, or you could use a ceramic chuck for the calibration substrate and then use some isolation for the the main wafer. So for adapters, then you can adapt the module to other connections such as coax 1 millimeter and 0.8 millimeter and waveguide WR5 waveguide. And so those adapters are also available that interface directly with the module in order to adapt the module for different applications. The VectorStar broadband system uses a modular architecture that allows for increasing the number of ports. For example, you could start off with a 2-port 110 system, and by adding a multi-port test set plus the additional modules, you can reconfigure for a 4-port broadband system. The 220 system uses the same modular architecture, so the possibility to increase from a 2-port 220 to a 4-port 220 would exist by adding the additional test set and additional modules. So that's a quick overview of our system, and I hope that it gives you a better feel for how we approach broadband system measurements and how we're able to combine all the capabilities of the previous systems and advance it to a 220 gigahertz module, and giving you the ability to do single sweep connections from 70 kilohertz to 220 gigahertz. Okay, thank you for your attention, and I look forward to talking to you further about this system.